Welcome back, and in this video we're going to introduce another couple fun properties in relation to trigonometry. Okay, and we saw a lot of sines before in the area. Now we're going to do another law and another formula. But before we go on, I'm just kind of curious. I want you to look back at the examples that we did and ask yourself, okay, in the setup for law of sines, what sort of information was given to you? Okay, so take a minute, pause the video, and look back and say, okay, law of sines, what was given to me? This, this, and this. Generally, I think that you might find that it falls into one of two camps. You could have angle, side, angle. Okay, so angle and then the side and then the other included angle. You could also have been given side, side angle. Okay, so you could have had that set up as well. Okay, and I believe that's you actually could have had side angle angle too. Okay, that could have worked as well. Okay, so one of those three generally work. Okay, so from geometry, you're probably seeing like, oh my God, we're doing all this first again. No, 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 just the setup. But remember, there were other types of congruences too. There was side, side, side congruence, and then there was side angle side congruence too. So we haven't seen these yet. So maybe there are different setups for those. Huh. Okay. So I'm kind of wondering, okay, what else can we do with this? So what I'm going to do is I'm going to look at that obtuse triangle again that we use for law of sines to prove that, and look at it this time from a coordinate geometry perspective. Okay, so I'm going to put one coordinate at the origin, and then I'm going to put another coordinate here and another coordinate here. Okay, and I'm going to call this point or vertex C, this is going to be vertex B, and this is going to be vertex A. Okay, and as points, again, this side length would be C, so then that means that this point here would be C comma 0. This point, we don't know what it is, but we can say, okay, well, you go over some unit X, and then you go up some unit Y, so this would have a point of XY. Okay, and so, okay, this is still may be useful, and again, we would still call this side length A and this side length B. Okay, I'm kind of curious about looking at A though. Okay, so if I want to look at the side length of A, right, to find the length of that, okay, I'm in coordinate geometry, I can use a distance formula. Let's use the distance formula. Okay, so distance formula, okay, difference in the x's, oops, that should be a C, squared plus difference in the y's. Okay, fine. And then simplify, maybe get rid of the square, so let's call this a squared instead. Big deal. X minus c squared plus, okay, that's just y squared. Okay, now I'm stuck. Well, okay, let's remember now, with the inclusion of y, right, I get a right triangle. And so in this right triangle, right, if I look at this and I call this angle theta, actually let's call it just angle A, because it is in fact angle A. So let's say that, you know, that cosine of A is equal to x over b. Okay, that's a fine statement. And similarly, sine of A is y over b. Okay, that's fine. Why is this useful, Professor Bright? I don't know yet. Well, okay, I have x and y. Maybe it's useful to solve for x and y. Okay, so this would be b cosine A is equal to x, and then similarly here, y is equal to b times sine of A. Okay, great. Okay, let's substitute those in because I can work with sine and cosine of an angle. Okay, and so then I'm going to have, you know, a squared is equal to parentheses, and now I'm going to substitute b cosine A, and then minus c all squared plus, and then parentheses here, b sine A. Okay, and I'm going to square all that. Okay, and now I'm going to pause the video and write a few more steps. I'm just going to do the algebra. So do the algebra, And so here's the simplified algebra. So I just expanded all this out in the first step. Second step, I collected the terms with b squared in them. So I factored out a b squared, and then I had cosine squared plus sine squared, and then just kind of rearranged the other stuff. And cosine squared plus sine squared is 1, right? And so, boom, there we are. And this, my friends, is indeed one form of the law of cosines. Okay, so this is really kind of an interesting result. You can, of course, change out a, b's, and c's. So this would be b squared is equal to a squared plus c squared minus 2ac cosine of b. The big thing is that when we think about this, this is b squared, so at least in the black version, so it'd be b squared plus c squared, which would be this entire side length here, and then minus 2bc, and then cosine of the included angle. So really, for law of cosines, you should have either all three sides, right? So you can have that, or you need two sides and the included angle. Okay, so that fits our all three sides, or two sides and the included angle. So really, law of cosines is when you're going to use these two things. Okay, so let's just kind of get a quick little example in here. Okay, I'm going to leave that for reference. Triangle ABC. Okay, I don't know exactly what it looks like, so maybe it's like this. Maybe I'm wrong. Let's call this ABC. And so then here I know that this is, oops, not there. Angle B is 61 degrees. A is 28, C is 19, so then I want to solve this, right? So I can use law of cosines to find the other side, right? Can I use law of sines? Not yet. So let's go ahead and use law of cosines. Okay, and so this is going to be, okay, let's call this, what is this, b squared? And b squared is equal to a squared, so 28 squared, plus c squared, 19 squared, minus 2 times a times c times cosine of the included angle. Okay, and now we get out our fancy dancy calculators and calculate away, and you get 25.1 degrees or so. Okay, so great, we know that side. 25.1, and that's not degrees, my bad. That's just a side length, right? And okay, so then now at this point I know all the sides, and I can use whatever mechanism I want. I could use law of sines if I wanted to. So let's say I wanted to find angle C, so I do sine of C over 19 is the same as sine of 61 is to 25.1, and then I can get C as 41.6 or 41.5 degrees or so, and then just by doing or making sure that all the angles add up to 180, you end up with angle A as about 77.5 degrees. Okay, so that allows us to complete the triangle. Okay, so and again, you didn't need to use law of sines here. You could have used law of cosines to figure out the angle as well. Okay, so great. Now, law of cosines actually leads to another formula for the area called Heron's formula. Its proof does use law of cosines, and it is in the book, or you can, Google that thing. And the big thing here is that it's defined as a square root with this s thing in it, and the s is called the semi-perimeter. It's really just perimeter over 2, okay, because perimeter, and then you take 1/2 of it, okay. So if we were to use our previous triangle, again, the side lengths were 28, 19, and then 25.1, then the semi-perimeter, you add them up and divide by 2, and so then we get 36.05, so then the area here would just be square root 36.05 and then 36.05 minus 28. This one, it is a little tedious with the calculation, but it is okay. Minus 36.05 and then times 25.1 minus 36.05. Okay. Oops, I have these backwards, don't I? 36.05 minus 19, and then this should be the other way around, 36.05 minus 25.1. And when you do that calculation, you get the area is 232.8-ish units squared. Okay, so just a quick example using Heron's formula, and then again reminding us of the law of cosines. Okay, so make sure to jot that down if you don't have it down already.